Yum, cabbage soup. Well, not exactly, but I am heating some of my purple cabbage in water so that we can do some fun acid-base chemistry. Our study today involves acid-base indicators and the pH scale.
In this lesson, you will define acid-base indicator, identify substances as acids or bases using various indicators, describe the pH scale, and make calculations involving pH, the concentration of hydrogen ions, and the concentration of hydroxide ions for a given solution.
In the last lesson, we learned how to classify substances as acids and bases based on the Arrhenius definition and also based on an operational definition. Don't forget that we discussed that there are a couple of additional definitions for classifying acids and bases, but we are sticking to the basics. Today, we are going to look more closely at one of the properties listed in our operational definition of acids and bases. We said that both acids and bases turn acid-base indicators different colors. To really understand what we are talking about, you need a definition of acid-base indicators.
An acid-base indicator is a substance that changes color depending on whether it is in the presence of an acid or a base.
There are many indicators available to help us determine if a substance is an acid or a base. Different indicators work best in different pH ranges, but we'll get into that more shortly. For now, let's do a little experiment to illustrate the use of indicators. I'm going to test some of the acids and bases that were used to develop our operational definition in the last lesson. I'm going to test each one with a set of 4 different indicators: litmus paper, phenolphthalein, bromothiamyl blue, and my personal favorite, cabbage juice. On your note-taking guide, you will write down the color change for each of the indicators. First, we are going to test each of the acids and bases with litmus paper. There are 2 types of litmus paper, red and blue. In your chart, write R arrow B if the red paper turns blue, B arrow R if the blue paper turns red, and NC if there is no change. I'm going to start by putting both pieces of litmus paper into the HNO3. Record the color change. Now, let's test the NaOH. Next is the KOH. And finally, the H2SO4. Now that I have rinsed the well plate and replenished the samples of acids and bases, let's put a few drops of phenolphthalein into each solution. Note the color change in your chart. Again, write NC if there is no change. The first solution tested will be HNO3. The second solution tested is NaOH. Now I'll drop the phenolphthalein into the KOH. And finally, the H2SO4. Now, I'm going to follow the same procedure to test the solutions using the indicator bromothiamyl blue. Be sure to record the color change in your chart. First, I'll put a few drops of bromothymol blue into the HNO3. Now, I'll test the NaOH. Next is the KOH. And finally, the H2SO4. The last indicator that I'm going to use is good old cabbage juice. If you boil purple cabbage in water, the purple dye in the cabbage leaves will color the water, like this. Cabbage juice makes an excellent acid-base indicator. You'll find that there are many things in nature that are acid-base indicators. Did you know that a certain type of flower is blue if it is grown in acidic soil and pink if it's grown in basic soil? Amazing. Don't forget to record the color change on your chart as I drop this cabbage juice into each of the solutions, starting with the HNO3. Now, I'll test the NaOH. Next, I'll test the KOH. And finally, the H2SO4. You should have your data chart completely filled in with the color changes from the various indicators. Next, you are going to complete the conclusion questions for the lab and discuss these as a class. Then, you are going to do a little lab of your own to determine whether some common household substances are acids or bases. When you have finished that, I'll be back to discuss the difference between the concentration of an acid or base and the strength of an acid or base.
Local teachers, please pause the tape for your students to complete the conclusion question for the indicator lab section of their note-taking guide.
I bet you had fun experimenting with those household substances and acid-base indicators. I always do, even though it drives my wife crazy. You may be asking, why do we need so many different indicators? Actually, this is just a small sampling of the available indicators. Each one works best in a certain pH range. We'll discuss pH in detail in just a bit. Simply put, the pH scale deals with both the concentration of the acid or base and its strength. I don't want you to confuse the two terms. The strength of an acid or base is determined by how well the acid or base dissociates in water. Strong acids and bases dissociate completely, whereas weak acids and bases only dissociate partially in water. Remember from our operational definition that acids and bases are both electrolytes. This property is directly related to the strength of the acid or base. We discussed in Unit 10 that the reason electrolytes conduct electricity is because they dissociate in aqueous solutions to yield ions. It is the ions in the solution that carry the charge. A strong acid or base will dissociate to yield more ions, which will produce a stronger current than a weak acid or base. Let me demonstrate this for you. Here, I have a sample of the same concentrations of a strong acid, HCl, and a weak acid, HC2H3O2. I'm going to place identical conductivity testers into both acids. Observe. Notice how much brighter the bulb lights up when it is placed in the strong acid. It even blinks.
A strong acid dissociates completely in water. One example of a strong acid is hydrochloric acid, HCl. When HCl is in an aqueous solution, all of the hydrogen ions will separate from the chloride ions. And all of these ions conduct a current well. A weak acid only dissociates partially in water. An example of a weak acid is acetic acid, HC2H3O2. When acetic acid is in an aqueous solution, some of the hydrogen ions separate from the acetate ions, but most of them stay attached. Since there are relatively few ions in the solution, the current is poorly conducted.
Now I'm going to repeat the conductivity test with a strong base, NaOH, and a weak base, NH4OH. Just like the acids, you see that the strong base lights up the tester more brightly and makes it blink.
A strong base dissociates completely in water. Sodium hydroxide, NaOH, is an example of a strong base. When NaOH is in an aqueous solution, all of the sodium ions will separate from the hydroxide ions, and all of these ions conduct a current well. A weak base only dissociates partially in water. Ammonium hydroxide, or ammonia, NH4OH, is an example of a weak base. When ammonia is in an aqueous solution, some of the ammonium ions separate from the hydroxide ions, but most stay attached. Since there are relatively few ions in the solution, the current is poorly conducted.
The thing you have to remember is that both strong and weak acids, as well as strong and weak bases, can be diluted. If you take any acid or base and add it to water, you will decrease the concentration of that acid or base, just like we studied in our unit on solutions. Both the strength of the acid or base and the degree to which it has been diluted determine the concentration of the acid or base. So, why should that be important to you? As it turns out, the concentration of an acid or base is very important. For example, our bodies are full of acids and bases, and it is critically important for the concentration of these acids and bases to be correct for our bodies to function properly. For example, our blood is slightly basic. If the concentration of the base in our blood drops too low, a condition called acidosis develops that could lead to fainting spells and even a coma if the condition is not corrected. Since it is so important to keep track of the concentrations of acids and bases, those smart chemists have found a way to measure the concentration of acids and bases. It is called the pH scale.
The acidity of a solution can be expressed in terms of the solution's pH. pH is based on the concentration of hydrogen ions in the aqueous solution. It is calculated by taking the negative logarithm of the hydrogen ion concentration. The brackets in the formula represent concentration. A solution with a higher hydrogen ion concentration will have a lower pH value. Acids have pH values between 0 and 7. Bases have pH values between 7 and 14. Neutral substances, such as water, have a pH of 7. Some other acids and bases you are familiar with include apple juice, which has a pH of 3, and household ammonia, which has a pH of 11.
Let's go ahead and try a pH problem. But first, we'll need our math hats. We're going to use the formula pH is equal to the negative logarithm of the hydrogen ion concentration of a solution. To begin with, we're going to limit our calculations to strong acids. Do you have any idea why?
Since strong acids dissociate completely, if we know the concentration of the acid, we can figure out the concentration of the hydrogen ion.
Exactly. Let's give that a try. Determine the pH of a solution of HCl that has a molarity of 1 times 10 to the negative 4th power. Well, since there is one hydrogen ion in every formula unit of HCl, the concentration of hydrogen ions is the same as the concentration of the solution. So we plug into our formula, pH equals the negative log of 1 times 10 to the negative 4th. You should have a log button on your calculator. On some calculators, to calculate the log, you'll need to push the log button first and then enter the number. On other calculators, you'll need to enter the number first and then push the log button. Either way, use that log button to calculate the log of 1 times 10 to the negative fourth. To enter the 10 to the negative fourth, you may also need to use the EE button on your calculator. Once you calculate the log of 1 times 10 to the negative fourth, you should get negative 4. But remember that pH is the negative log. So it's the opposite of negative 4, which gives you 4. Your local teacher is going to pause the tape for you to try and figure this out on your own calculator. Once you've mastered that, I'll give you a problem to try on your own.
Local teachers, please pause the tape now for your students to try this problem on their calculators.
Now that you have conquered your calculator, work this problem while my students do the same. Calculate the pH of a solution of HNO3 with a molarity of 1 times 10 to the negative 3. How did you do? You should have found that this solution has a pH of 3. Let's try one more before we move on. Calculate the pH for a solution of H2SO4 with a molarity of 1.0 times 10 to the negative fourth power. In this case, there are 2 hydrogen ions for every formula unit of H2SO4. So the hydrogen ion concentration is going to be 2 multiplied by 1.0 times 10 to the negative fourth power, or 2.0 times 10 to the negative fourth power. So we take the negative log of this number and find the pH to be 3.7. Your local teacher is going to have many more of these for you to practice, but now you should learn how to calculate the pH for a strong base.
Even the most acidic solutions contain some hydroxide ions, and even the most basic solutions contain some hydrogen ions. At every pH, the concentration of hydrogen ions times the concentration of hydroxide ions is equal to 1.0 times 10 to the negative 14th power. To calculate the pH of a base, you start by using this relationship to calculate the concentration of hydrogen ions, and then use the formula pH equals the negative logarithm of the concentration of hydrogen ions.
Let's give one of these a try. Let's calculate the pH of a solution of NaOH with a molarity of 3.0 times 10 to the negative second power. Since there is 1 hydroxide ion in every formula unit of sodium hydroxide, we have a hydroxide ion concentration of 3.0 times 10 to the negative second molar. Using the relationship that the concentration of hydrogen ions times the concentration of hydroxide ions is equal to 1.0 times 10 to the negative 14th power, we can solve for the concentration of hydrogen ions. 1.0 times 10 to the negative 14th divided by 3.0 times 10 to the negative second is 3.3 times 10 to the negative 13th. We take the negative log of that to get a pH of 12. That wasn't so bad, was it? Now, you give it a try.
Find the pH for a solution of CaOH2 with a molarity of 1.0 times 10 to the negative fourth power. Local teachers, please pause the tape now for your students to solve this problem.
I'm sure everyone figured that one out. As always, you'll have plenty more to practice. But let's try one more type of problem together before we call it quits for the day.
Calculate both the hydrogen ion concentration and the hydroxide ion concentration for an aqueous solution that has a pH of 4.0. pH equals the negative logarithm of the hydrogen ion concentration of the solution. Let's plug in what we know. Before we use the calculator, let's move the negative sign to the other side. To solve this on your calculator, you type 4.0, then the negative sign, then the second or inverse button, and then the log button. So, the hydrogen ion concentration is 1.0 times 10 to the negative fourth power. We know that the hydrogen ion concentration times the hydroxide ion concentration is equal to 1.0 times 10 to the negative 14th power. We plug in the hydrogen ion concentration and do the math. Divide 1.0 times 10 to the negative 14th power by 1.0 times 10 to the negative 4th power to get a hydroxide ion concentration of 1.0 times 10 to the negative 10th power. Finally, don't forget that your unit is molarity for both the hydrogen ion concentration and the hydroxide ion concentration.
Well, our math hats are begging for a break, so I think we'll stop for now. Of course, you will continue practicing these after I'm gone. For now, the chemistry quiz.
Cumulative review question number 1. Solutions that conduct a current are called A. Electrolytes, B. Non-electrolytes. Cumulative review question number 2. Antifreeze raises the boiling point of water in a car's radiator. A. True. B. False. Number 1. Which of the following would occur in an acidic solution? A. Blue litmus paper would turn red. B. Red litmus paper would turn blue. C. Phenolphthalein would turn hot pink. D. Cabbage juice would turn green. Number 2. A solution of HI is tested with a conductivity tester and produces a bright, blinking light. This would indicate that HI is A. a strong acid, B. a strong base, C. a weak acid, D. a weak base. Question number 3. Calculate the pH of 1 times 10 to the negative 5th molar solution of HNO3. A. 9, B. 14, C. 5. Number 4. What is the hydrogen ion concentration of a solution with a pH of 12? A. 1 times 10 to the negative 12, B. 1 times 10 to the negative 2nd, C. 1 times 10 to the negative 14th. And finally, number 5. The solution described in number 4 would be A. acidic, B. basic, C. neutral.
You have to be careful with your cabbage juice. It stains stuff easily, so dispose of it carefully. Don't do this at home, kids. You'll regret it. Next time, we'll talk about what happens when we react an acid with a base.